Okay, before we could talk about the math with acids and bases, we'll talk about concentration. What do we think concentration means? Yeah, how much of something there is. So more formally, concentration measures the amount of solute dissolved in a specific volume or mass of solvent. So if we think about like salt water, for example, the salt is called the solute, the water is called the solvent, and all together we have a solution. For those of you who have started on that one-page summary that's due on Sunday, these terms probably came up again for you. Concentration is also known as molarity, and molarity has the units of moles per liter. Anytime you see a capital M, that's the same as moles over liters. Also, if we see these square brackets, that means concentration. Today, we're really going to be focusing on the concentration of hydroxide. From last class, we know hydroxide is synonymous with bases, and we're going to be looking at the concentration of hydrogen or hydronium. These two terms mean exactly the same thing, hydrogen and hydronium, and those are correlated with our acids. So we have hydroxide with our bases, and we have hydronium with our acids. So we're going to be working on calculating concentrations as well as pH and pOH. In the self-ionization of water, what happens is two water molecules come together and they're going to form a hydronium and a hydroxide. Like water is neutralizing itself and breaking apart. At 25 degrees Celsius, the concentration of hydronium is this value here, 1 times 10 to the negative 7. We see that capital M, which represents concentration. And the concentration of hydroxide is 1 times 10 to the negative 7 as well. They're the same value. So when we multiply them together, we get something called Kw, which is the ionization constant of water. It's the hydronium times the hydroxide, and it always equals 1 times 10 to the negative 14. When your concentration of hydronium equals the concentration of hydroxide, remember hydronium is the same as just H plus, or like our protons. If they're equal to each other, it's going to be a neutral compound. We know when we talk about the pH scale at the middle for 7 is neutral. If the hydronium, or just the hydrogen, is greater than the hydroxide, that's considered acidic. And in comparison, if hydroxide is bigger than just the hydrogen or hydronium, that's going to be known as a basic solution. So let's do some calculations with that Kw. Our strong acids and strong bases are going to completely ionize. Ionize means break apart or dissociate. If we had NaOH, that's a strong base. We talked about naming bases last class. That's called sodium hydroxide. When sodium hydroxide is placed into water, it breaks apart into the sodium ion and the hydroxide ion. I kept the hydroxide together. I didn't split apart the oxygen and the hydrogen. It's a polyatomic. It's going to stay together. I know the concentration of the entire compound is 1 times 10 to the negative 12.
I
That's given to
accidentally wrote
you in the
minus 12
question.
and it should be minus
So
2.
when it breaks apart, if there's no coefficient in the front, the concentration of those ions will be exactly the same. So the sodium is 1 times 10 to the negative 12, and the hydroxide is also 1 times negative 12. So I want to figure out my hydronium, also known as the hydrogen concentration. I just saw that formula before that said that Kw equals the hydroxide times the hydronium. And when I multiply those two concentrations, they always equal 1 times 10 to the negative 14. So I can fill in the one that I know. I know right here the hydroxide concentration, so I'll plug that into the formula. 1 times 10 to the negative 12. I don't know the hydronium concentration, so you can rewrite that, or you can think about it as X. All right, so I just plugged in an X for the hydronium concentration. I don't know that. You could just rewrite that as well, but if it confuses you, just write it as an X. When I multiply hydroxide times hydronium, it always equals 1 times 10 to the negative 14. Then, if I want to isolate my X or my hydronium concentration, I'll just divide both sides by that 1 times 10 to the negative 12. When I do that in the calculator, what I'm solving for is that hydrogen concentration, which is going to be 1 times 10 to the negative second power. And because it's a concentration, I should always have the units of capital M. So if I'm looking for hydroxide's concentration, I would just divide by hydronium's concentration. Or if I'm looking for hydronium, divide by hydroxide. So whichever one you know, take the 1 times 10 to the negative 14 and divide by that known value. So let's look at another one here. I'm given information about HCl, hydrochloric acid. When it's placed into water, it's going to break apart into the individual ions, which is H plus and Cl minus. They all have just a 1 coefficient, so whatever the concentration of the HCl is, which is told to me, will be the exact same concentration for those individual ions. I'm really focused on this hydrogen ion concentration, and we're trying to find hydroxide's concentration. I know that Kw equals 1 times 10 to the negative 14, and that's going to equal my hydroxide times my hydronium. This time, just a little bit different than the last one, I actually know the hydronium, but I don't know hydroxide. But we're going to solve that in the exact same way. I'm going to plug in the one that I know, and then just divide both sides by the one that we know. So I'm going to divide both sides by 2 times 10 to the negative 4th. Make sure that you're using that EE button to solve for your concentration. So 1E negative 14 divided by 2E negative 4. And the concentration of hydroxide is going to be 5 times 10 to the negative 11 with a capital M for the final units. Okay, we want to start with the dissociation equation. So we have the HNO3. It's going to break apart into your H plus and your NO3 minus. We're given the concentration of the solution, 1 times 10 to the negative 4. So is the concentration of hydrogen exactly the same as that value? Yeah, it's a 1-to-1 ratio, so it's exactly the same. And we already know our H3O plus then, the same exact value as the solution. And then we're going to figure out the hydroxide concentration. We've been using that 1 times 10 to the negative 14 and saying that's equivalent to the H plus or H3O plus times the OH minus. We have that H3O plus from above, so we'll just plug in that value. So 1 times 10 to the negative 4th equals 1 times 10 to the negative, this should be 14, I'm sorry, negative 4. And we're going to solve for OH minus. So we'll just divide both sides by that 1 times 10 to the negative 4th. So our concentration of hydroxide equals 1 times 10 to the negative 10, and that's a capital M because it's a concentration. So I first started with my dissociation equation and broke it apart into the hydrogen and the nitrate. The solution's concentration will always be given, and that's exactly the same as the hydrogen, as long as there's no coefficient out here in the front. Then I plugged in that hydrogen concentration to my Kw expression. Kw always equals 1 times 10 to the negative 14, and I divided by the concentration that I knew. Here's another formula. I would definitely highlight, circle this formula. The pH equals the negative log of the hydrogen concentration. So on your calculator, make sure you locate the negative button, the log button. I'd also like for you to find the exponent button, not the EE button, but just like a regular exponent. Usually it's that upside down caret or like x to the y. make sure that you know where all of those buttons are on your calculator. So let's try one of these problems with this formula. So what's the pH of this concentration? Now first, I'm going to start with a dissociation equation. This is going to break apart into the sodium and the hydroxide. I'm given the concentration of the sodium hydroxide, and because they're all just ones in the front, my hydroxide concentration will be exactly the same. The formula that I just said is that pH equals the negative log of the hydrogen concentration. Is this the hydrogen concentration? No, but we just used that Kw 3 times, and we said the hydroxide times the hydrogen equals Kw. So let's fill in what we know. I know that Kw is always 1 times 10 to the negative 14. I don't know the hydrogen concentration. I want to figure that out. But I know that hydroxide is that 1 times 10 to the negative third. I'll divide both sides by that 1 times 10 to the negative third for my hydrogen concentration, which is going to be 1 times 10 to the negative 11. Now that I know the hydrogen concentration, I'll do the negative log of that value. If you know where the answer key on your calculator is, like the A and S button, it'll be really helpful for this unit because you're going to oftentimes be using the value that you just previously got. So I'm going to do the negative log of 1e negative 11, and it comes out to a pH of 11. Their formula that I'd like for you to highlight, circle, write down. If we know the pH, we could find the hydrogen concentration by doing 10 to the power of negative pH. So wherever that exponent button was and negative, make sure you're not using the subtraction symbol, but the negative. So let's try this. We know the pH is 3, and we want to find the hydronium concentration, which is same as the H+. Okay, so we know the formula is going to be 10 to the negative pH. So our pH is 3, so we're simply going to do 10 to the negative third power. You should have this in scientific notation, so if you put that in your calculator and you have it in scientific notation, it'd be 1 times 10 to the negative 3. It's a concentration, so you want that to be a capital M. So really simple process, just 10 to the negative third, put that in your calculator, and that's your hydrogen ion concentration. Another formula looks really similar to one we just saw, but this one is POH equals the negative log of the hydroxide concentration. The one we previously saw was about the pH is the negative log of the H+. So let's use this formula to find a POH. I know that the hydroxide concentration is this value here. The formula says that the POH equals the negative log of the hydroxide concentration. I'll plug that in. And in the calculator, we're typing the negative log of 1e negative 4. In this case, the POH is 4. pH and POH will be numbers between 0 and 14 because our pH scale is from 0 to 14. For all of the calculations we're doing, let's round to just 2 decimal places for all of these calculations. Another formula that looks familiar, this time, if we want to find the hydroxide concentration, we'll do 10 to the negative POH. A little bit different, the hydrogen concentration was 10 to the negative pH, and this time we see that with POH. So if we know the POH, we could find the hydroxide concentration by doing 10 to the negative POH, or 10 to the negative fifth power. Because it's a concentration, I do have to put an M. All of these values have been pretty simple. Sometimes you actually do need to plug it in your calculator and do 10 to the power. And finally, we know that pH So pH plus POH equals 14. If we're missing either one, we can find the other. So pH plus POH equals 14. If pH is 9, what's the POH? 5. So that one's definitely the simplest. The formulas that we saw, we'll go over them in a second. Let's just try one more. So determine the hydronium ion concentration. Hydronium is that H3O plus or H plus, they're the same thing, of an aqueous solution that has a pH of 4. So any formulas that really relate pH and the hydrogen concentration. What's the formula? (10 to the negative pH. So 10 to the negative 4. And I want to write that in scientific notation, 1 times 10 to the negative 4. And that's a molarity, so a capital M. Let's kind of recap the formulas that we saw today. The most basic is the one we just saw. pH plus POH equals 14, always. We also said that Kw always equals 1 times 10 to the negative 14, and that equals my hydrogen times my hydroxide. So I can use that to find a hydrogen concentration that's missing or a hydroxide concentration that's missing. We also said that pH equals the negative log of the hydrogen concentration. But if I already know pH, I could find the hydrogen concentration by doing 10 to the negative pH. And conversely, I could find POH by doing the negative log of the hydroxide, or I could find the hydroxide concentration by doing 10 to the negative POH. So these are the main formulas that we're going to be using today, and they kind of go around in a square. So let me show you what that square looks like. They're the same exact formulas that I just had. Let's say that we have pH and we want to find POH. I would simply do 14 minus the pH. So the direction of the arrow makes a difference. Once I have the POH, I could find the hydroxide concentration by taking 10 to the negative POH. And then I can also find the hydrogen concentration by taking that Kw divided by hydroxide. So they all relate to each other. I can start with just one value and find the other three by going around in the square. It doesn't matter where you start. I think the easiest thing to do if you're ever given a pH, right away find your POH because they add up to 14, or vice versa. If you're given a POH, you'll find your pH by subtracting from 14 and just keep going around. So you have practice in your packet. Go ahead and look at the practice. You have one that's questions and one that's like a chart. I would start with the chart. I think it's a little bit easier to get used to. And definitely look at this as you're working on that. I don't want you to get too reliant upon this square because you're not using this square on like a quiz or a test. But if you're starting with pH, like in the very first line, I could find my POH by subtracting from 14. Then I could come over to find my hydroxide, go up to find my hydrogen concentration. Then we also in the final column want to figure out, is it acidic or basic? How would you determine that? The pH. If it's less than 7, that's acidic. If it's higher than 7, that's basic.